All right, so now the last thing we're going to do with polar coordinates is we are going to learn how to convert into polar coordinates from rectangular coordinates, okay? Now, we've got a little bit of groundwork to do before we actually do an example, okay? So this is, converting into polar coordinates is a little more complicated. One of the reasons for that is because we are going to have to use sine inverse and cosine inverse in order to solve for a theta angle. Now, I don't know if you recall, but when you use sine inverse and cosine inverse, because sine inverse of theta will only give you answers that are between negative pi over 2 and pi over 2. So the problem here is, well, what if the actual theta angle is not in the fourth or the first quadrant? Or what if it's in the fourth quadrant? We don't want a negative one. Look, all of our theta angles have to be between 0 and 2 pi. So sine inverse is actually only going to give you a correct theta angle if the point is in the first quadrant, if it's a positive, x and y. Cosine, similarly, will give you a correct answer, will give you a correct theta angle between 0 and pi, right? So if it's in the first or second quadrant, cosine will give you a correct answer, but if it's in the third or fourth quadrant, cosine will not give you the correct theta angle, okay? And so because of that, the first thing you have to consider is, the first thing you have to ask yourself is, what quadrant is this point in? Well, that's easy to determine because if the point you're given, if the xy coordinate that you're converting from, if it's like negative 3 and negative 5, well, you know that this is in the third quadrant. So the very first thing that you have to do to make this conversion is you have to identify the quadrant. Well, let's do that. We usually do quadrant in capital. Identify the quadrant of the point. Okay? Now, if the quadrant, I'm going to make some notes over here, if the point is in quadrant 1, we know that our theta angle has to fall between 0 and pi over 2, okay, or 1.57, right? In fact, let's go ahead and do these in, I'm going to do them in decimals, because a lot of our answers are going to come out in decimals. They're not really going to come out in with pi included. If it's a quadrant 2 point, by the way, a quadrant 1 point will be a positive point. A quadrant 2 point will be a negative positive point. And our theta angle is going to fall between 1.57 and approximately 3.14, right? Because that's pi. If it's a quadrant 3 point, and you'll know it's a quadrant 3 point if it's a negative coordinate, okay, then it's going to fall between 3.14 and, I always forget this one. I know I shouldn't, but I do, and 4.71. All right, and then if it's a quadrant 4 point, and you'll know that it's a quadrant 4 point if it's a positive x and a negative y, then it's going to fall between 4.71 and 6.28, which is approximately 2 pi, right? All right, so you're going to need to write this stuff down. Now, if you wind up getting a theta angle that is negative, meaning less than 0, or larger than 6.28, you really shouldn't get one that's larger than 6.28 because, our angles, our sine inverse will give you a negative, but only up to pi over 2, and cosine will only give you up to pi, okay? Or cosine inverse. So if you get a negative one, what you basically have to do for sine is if you get a negative theta angle, you need to add 2 pi. What that means is that it's in the fourth quadrant. And so you have to add 2 pi, and then you'll get one up here. But even from there, you might have to then convert it over to the third quadrant. So when doing this thing, you're going to have to convert, know where where your point is, which quadrant it's in, and then use what you learned about converting from one quadrant to another to make sure that you get the correct theta angle, okay? So that's the first thing we're going to do, is we're going to identify the quadrant of the point, okay? All right, so the second thing we're going to want to do is we're going to need to identify R, okay? So we're given, let's go ahead and put up, we were working on that point 4, 2, right? So let's go here, 1, 2, 3, 4, 1, 2, right? This is the point 4, 2. And so let's say we want to convert the point 4, 2 into polar coordinates. We need a radius and a theta angle, okay? So the problem here is that we can use our formulas and we can put a 4 in for x and we can put a 2 in for y, but here's what we come up with. We get 4 equals r cosine of theta and 2 equals r sine of theta, okay? So the problem here is that in both of these cases, we still have two variables that we have to solve for, okay? And basically, you can't just take these two formulas and simply just solve for r and then solve for theta, okay? We don't have a separate formula for theta and a separate formula for r the way that we did for x and y, okay? And so here's what we have to do. We have to solve for radius. Well, do you remember me saying that the radius is the distance from the origin to the point, the straight line distance from the origin to the point? And here's what I need to tell you, is that you know what that basically is? That is basically the hypotenuse of a right triangle. Because if we draw our x distance here, that's 4, and our y distance here, that's 2, we now have a right triangle with a hypotenuse. And we can now use the Pythagorean Theorem. But instead of calling the hypotenuse C, we're going to call the hypotenuse R, okay? Instead of calling one of the legs A, we're going to call it X. And instead of calling the other leg B, we're going to call it Y. So here, Y is equal to 2, X is equal to 4, and the hypotenuse is equal to R. So the Pythagorean Theorem would say that A squared, or X squared, plus B squared, or Y squared, is equal to C squared, or R squared. So we're going to work off of this. X squared plus Y squared equals R squared. And that is how we are going to be able to identify R. Now we can shortcut this just a little bit. If we know that to solve for R, we're going to have to take the square root here, and that means we'll have to take the square root over here, and that means that our solution for R is always going to be equal to the square root of x squared plus y squared, okay? And so to identify R, we're going to use the formula. I'll put this down here. R is equal to the square root of x squared plus y squared. And that is pretty much our last formula here that we're going to need for this, okay? All right, and so that is going to always be our second step, is to identify R. And remember, R is always going to be equal to the square root of x squared plus y squared, okay? And we're going to solve this in just a little bit, okay? So now, after you have R and you've identified the quadrant, the third thing you're going to do is you're going to use one of these. You only need one of the two formulas. You're either going to use the x equals r cosine of theta formula, or y equals r times sine of theta. Okay? Because here's the thing. You've already solved for r. Okay? You know what x is. So now you only need one of the formulas to solve for theta. Okay? Or you know what y is, you know what r is, and you can just use that one to solve for theta. You do not need to solve for theta in both of these formulas. You only need to solve for theta in one of them. So whichever one looks easiest to you. I'm a fan of cosine, because cosine never gives me, remember how we said that cosine will give you an answer from 0 to pi, but sine will sometimes give you a negative theta angle. And so I prefer to use cosine over sine. okay, but if you may prefer sine over cosine. And then once you have decided which of these two you're going to use, the fourth thing you're going to do is you're going to plug in your known values and solve for theta. Plug in known values, and solve for theta, okay? And then lastly, step 5, you may need to convert theta into correct quadrant. All right. Okay, so let's say we have this point 4,2, okay? And so what we're going to need is we want to convert this. This is our x and our y, and we want to convert them into polar coordinates, okay? Let me go ahead and mute this. There we go. And so step 1 is identify the quadrant of the point. Well, point 4,2 is in quadrant 1, right? So up here, I'm going to say quadrant 1. Now we're going to have to identify the radius, okay? So the radius of the point for the rectangular point 4,2 is going to be equal to the square root of x squared, so that's 4 squared, plus y squared, that's 2 squared. So r is equal to the square root of, this is 16 plus 4, that's 20. And so r is equal to the square root of 20, which can actually be reduced to, this is the square root of 4 times the square root of 5. So it can actually be reduced to 2 square root of 5, okay? But we can also convert it into a decimal, and we'll go to 2 decimal places on this. Let's just key in the square root of 20. And so the square root of 20 is approximately equal to 4.47. Okay, so 4.47, okay? Now, I'm actually going to put up here, I'm going to put r is equal to the square root of 20. Now let me tell you why. You can put 4.47 in for an answer in a box on the quiz online. Okay, that's fine. But when we come down here and solve for theta in one of these formulas, we cannot put 4.47 in for r. 4.47 is an approximation. We should not use approximations in solution formulas. When we are doing solution formulas, we should use precise values, which in this case is the square root of 20. Okay? So we're not going to use this 4.47 until we're done when we're putting the answer in. But in our formula, when we're solving for theta, we're going to use the square root of 20. Okay? It's very important for you to understand. Okay? There's a general rule in math that we never, ever, ever, ever round numbers until we get to the very end, the very last step. Okay? So if you're trying to solve, let's say you have a 3-step solution. Step 1, then 2, then 3, or let's say it's a 4-step solution. And you do something in step 1, you do something in step 2, and then you get a number in step 3, and then you round, right? Then you take the rounded number and plug it into step 4. It will make step 4 wrong. What you have to do is you have to go back to the unrounded number from step 3, put it into step 4, then you can round that number, then it'll be correct, okay? So we got to stick with precise values until we get to the very end, okay? All right, so radius is the square root of 20, even though when we put it in the final answer, we're going to put it in as a decimal. In our formula, we're going to put it in as the square root of 20. All right, so now we're going to use either the x formula or the y formula. I'm going to use the x formula because I like the x formula. So, and then go to step 4, plug in the known values. So for x, I'm going to put in 4. Then I'm going to have equals. R is the square root of 20 times cosine of theta, right? Okay? And so now what I'm going to do is I need to solve for theta. Well, the first thing I have to do is get rid of the r. So I'm going to divide by the square root of 20 and cancel. Over here I'm going to divide by the square root of 20. And so now I have 4 over the square root of 20 is equal to, now I'm not turning this into a decimal. I'm not going to turn this into a decimal and round it. I'm going to leave it as 4 over square root of 20 equals cosine of theta. Okay? Now, to cancel cosine here, I'm going to do cosine inverse to both sides. Cosine inverse cancels, and then over here I'm going to do cosine inverse. And so now what I have is theta is equal to cosine inverse of 4 over the square root of 20, which I can now key in the calculator. So my calculator, need to make sure I am in radian mode, and I'm going to go second cosine inverse, and I'm going to do 4 divided by the square root of 20. Okay, press enter, and here's what I get. I get theta is equal to now I'm rounding because I'm not using this number. I'm not plugging this number back into another part of the problem. We are at the end here. 0.46, that is the radian angle. Now, I need to make sure that 0.46 is a radian angle in the first quadrant. So if I go over here to the quadrant, sure enough, 0.46 is between 0 and 1.57, so that is correct. So I have my radius, I have my theta is equal to 0.46, and so now I'm going to put in polar coordinate r comma theta is going to be the square root of 20 comma 0.46 radians. Okay. Now when I enter it into the computer, now I can round my square root of 20, which is 4.47. So I have 4.47 comma 0.46. Okay. And these are the polar coordinates that match the rectangular coordinates 4.2. Okay. Let's go ahead now and look. Let's bring up the picture of the polar grid, and we'll see if that point looks like it's really close to 4.47 and 0.46. So we'll do this, and we will click forward here, and let's see where this point is right here. All right, well, its radius is 1, 2, 3, 4. It's a little more than, it's about 4.5, which looks about right. 4.47 is our radius. 0.46, this looks really close to pi over 6, but it's smaller than pi over 6. Let's see what pi over 6 is. Pi over 6 is 0.52, so 0.46 is a little bit less than that. Sure enough, a little bit less than pi over 6. That is, looks like these really are the correct coordinates, polar coordinates for the rectangular coordinates 4, 2. Okay? Let's try a couple more examples and see if you can get the hang of doing it yourself. All right, so here's an example. It says, what are the polar coordinates of the rectangular coordinates 7, 9? Okay? Why don't you pause the video, go through these 5 steps, and see if you can figure out the correct polar coordinates. Make sure your calculator is in radian mode. Okay? Go. All right, so now let's see how well you did. First thing I want to do is I want to identify what the quadrant of the 0.79. This is in quadrant 1 because it's positive, positive. So I know that I'm probably not going to have any problems. I probably won't have to do step 5 because it's already in quadrant 1. Okay? If it was in quadrant 3, I would definitely have to do step 5. If it was in quadrant 2, I would only have to do step 5 if I used sine. If it was then if it's in quadrant 4, I also definitely have to do step 5. So if it's in quadrant 3 or 4, definitely got to do step 5. All right, so now I need to identify the radius. So the radius is going to be equal to the square root of x squared, 7 squared, plus y squared, 9 squared. Okay? All right, so 7 squared, we got 49 plus 81. All right, 49 plus 81, that's 130. And therefore, the radius is equal to the square root of 130. Okay? And now I'm going to either use x or y. It doesn't really matter. Last time we did x. Let's go ahead and do y this time. So we're going to use y equals r times sine of theta. Okay, so in this case, y is equal to 9. So we'll have 9 equals r is the square root of 130 times sine of theta. And now we just need, so we've plugged them in. Step 4 here, we've plugged them in. Now we're going to solve for theta. We're going to divide by the square root of 130 on both sides. Cancel. And now we have 9 over the square root of 130 is equal to sine of theta. Okay, well, to cancel the sine and solve for theta, I'm going to need to do sine inverse to both sides. Sine inverse to both sides. It's going to cancel sine on this side, and we're going to have theta is equal to sine inverse of 9 over the square root of 130. So theta is equal to sine inverse of 9 over the square root of 130. Okay? We can do this in the calculator. Make sure it's in radian mode. So we're going to go sine inverse of 9 divided by the square root of 130. Okay? That's going to give me theta is equal to approximately 0.91. So, in fact, I'm going to get used to, something you may want to get used to doing is using the approximately equal to 0.91. Okay? And so, that means that our polar coordinates, I'm going to go ahead and convert the square root of 130 into a decimal. So square root of 130 is 11.4. So about 11.4 comma 0.91. 11.4 radius, 0.91 radians, and these are this 0.91 is between 0 and 1.57, so it is in the first quadrant, and that's why we didn't have to make a conversion. Okay. All right, now let's do one that is in maybe the third or the fourth quadrant. All right, so this one says, what are the polar coordinates of the rectangular coordinates -2, -3? Okay. All right, so the first thing we want to do is identify the quadrant of the point. This point is in quadrant 3 because it's a negative. And because it's in quadrant 3, we are definitely going to have to do some kind of conversion of theta in step 5. Now we're going to identify r, and so r is equal to the square root of x squared plus y squared. Now, these are negative values, so we're going to put them in parentheses, okay? So -2 and then square on the outside. See, in a calculator, if you do this in a calculator, I don't know if you figured this out already, if you key in -2 squared, it's going to do 2 squared first, then put the negative on it. It's going to tell you it's -4. And this is correct because this doesn't have parentheses. But if you did this, if it's the square of -2, -2 times -2, that's +4, okay? All right, so what we're doing is we're squaring this number with the negative. So it's -2 times -2, which is +4, okay? Plus -3 squared, okay? And so what we have here is we have -2 times -2 is 4. -3 times -3 is 9. And so we have 4 plus 9, that's 13. So the radius is the square root of 13, okay? So we've got our radius. Now we're going to use... let's go ahead and use the cosine. I want to use cosine, and then maybe we'll do an example with sine next time. So we're going to plug in our x value, which is -2. So we'll put -2 is equal to the radius, which is the square root of 13, times cosine of theta, right? Now we'll just start solving. We're going to divide by the square root of 13 on both sides. Okay, it's going to cancel, and now we got to cancel cosine. We got to do cosine inverse to both sides, right? Cosine inverse. That'll cancel cosine, and that'll bring down theta, right? Okay, and so we have cosine inverse of -2 over the square root of 13. Okay, so let's go ahead and do this in the calculator. We'll do cosine inverse of -2 divided by the square root of 13. And that's going to give us, see, here's the problem. This is going to give us a theta of approximately let's do approximately here. There we go. 2.16. The problem with this theta of 2.16 is that 2.16 is between 1.57 and 3.14. Okay? It's in the second quadrant. And that's because cosine inverse only gives us answers that are in the first or second quadrant. So what we now have to do is we need to turn this quadrant 2 theta angle into the equivalent angle in quadrant 3. Remember how we said a few lessons ago that that for every cosine, there's two answers for every cosine. So like in quadrant 2, we could have, in quadrant 2 up here, we can have negative square root of 3 over 2, but we also have negative square root of 3 over 2 in the third quadrant. Well, this is giving us our second quadrant solution for cosine. We need our third quadrant solution for cosine. And if you recall, I said a few lessons ago that you have to subtract your second quadrant solution from 2 pi in order to get your third quadrant solution. So what's really going to happen here is our real theta is going to be equal to 2 pi minus, now here's the thing, we can't subtract 2.16. We need to subtract what's actually in the calculator, which is approximately equal to 2.15879893. Why are you doing that, Mr. Ryan? Why can't you just do 2 pi minus 2.16? Well, it's because we don't want to use a rounded number. We want to get as precise a number as possible and then round that number. Okay? So we're going to go 2 pi minus this number right here, which is already stored in my calculator, and that gives me pi is approximately equal to 4.12. Now, it's possible that doing 2 pi minus this number still would have given us 4.12, but it also might not be. So let's go 2 pi minus 2.16. And sure enough, it did give me 4.12, but I'm warning you that you have to be very careful. Don't put rounded numbers into a calculation, okay? And so this is our theta angle, 4.12. It is in the third quadrant. It's in between 3.14 and 4.71. And our radius is the square root of 13, so we will then say 4.12, comma, and we could put, nope, that's the theta angle. Whoops, sorry about that. We're going to put the radius in first, which is the square root of 13. So you can either put square root of 13, comma, 4.12 radians, or we're going to convert our square root of 13 into a decimal, 3.61, radius of 3.61, and a theta angle measure of 4.12. Okay, and these are our polar coordinates for the that are equal to the rectangular coordinates of -2, -3. Okay, let's do one more example, and this one we're going to do in the fourth quadrant. All right, our last example here, we're going to what are the polar coordinates of the rectangular coordinates 4 and -5? Okay, so our first step is we're going to identify which quadrant. Well, we have a positive x and a negative y. That's the fourth quadrant. So we're going to go quadrant 4. Okay. Now we got to identify the radius, and so r is going to be equal to the square root of x squared, so that's 4 squared plus y squared, which is -5 in parentheses, then squared, right? Well, 4 squared, that's 16. -5 times -5, that's positive 25. So 16 plus 25, that's 41. So it's going to be the square root of 41, okay? Now we've got our radius. Now we need to either use x or y, so we're either going to do cosine inverse or sine inverse. Either way, it is not going to give us a fourth quadrant theta angle, okay? So we're going to have to make a conversion. For the fourth quadrant, I really like using sine because it will give me a fourth quadrant solution, but it'll be a negative angle. All I have to do at that point then is add 2 pi, and it's now a fourth quadrant theta angle. So I'm going to use the y formula. So y is equal to r times sine of theta. Okay, so y in this case is -5 is equal to r is the square root of 41 times sine of theta. Okay? Now we're going to divide by the square root of 41 on both sides. On this side it cancels. Now, to cancel the sine, we're going to do sine inverse over here. And on this side, we also have to do sine inverse. That'll cancel. And that'll mean that theta is equal to sine inverse of negative 5 over the square root of 41. So theta is equal to, I'm just putting the theta on this side of the equal sign and this on this side, sine inverse of negative 5 over the square root of 41. Okay? This I can now key into a calculator. So I'm going to do sine inverse of negative 5 divided by the square root of 41. And that gives me theta is equal to negative 0.9. Negative 0.9, basically. Okay? All right. Now, here's the problem. Now, technically, what I'm seeing in my calculator is actually negative 0.89. Theta is equal to negative 0.896055. Okay? All right, I'm writing that out because I know that I'm going to add 2 pi to this. So I don't even have to change this. All of my theta angles have to run between 0 and 2 pi. And this one is negative, so it's not between 0 and 2 pi. So what I need to do is I need to put it, now I know that this negative 0.9 is in the fourth quadrant, but it's a coterminal angle. So to find the one that's between 0 and 2 pi, I'm going to add 2 pi to go back around the circle, but I'm going to add 2 pi to this and then round. So I'm going to add 2 pi to this, and now what I get is theta is equal to 5.39. 5.39. Okay? And so this is my theta angle, and my radius is square root of 41. Now I can convert that into a decimal, and that would give me about 6.4. 6.4. So my coordinates, my polar coordinates are going to be radius of 6.4, comma, theta angle of 5.39, right? Oh, I forgot to, let's confirm. Is 5.39 in quadrant 4? Yep, it's between 4.71 and 6.28. And so these are the polar coordinates that match the same point as this point, 4 and negative 5, okay? All right, well, that's it. I'll have plenty of practice for you, plenty of opportunities for you to show your ability in doing this. You'll definitely get at least one quadrant 1, at least one quadrant 2, at least one quadrant 3, and at least one quadrant 4 point to convert over, okay, in the quiz.